Picture like a robot on a factory line, right? Its wrench breaks, so it fixes the wrench. Standard stuff. But what if it didn't just fix the wrench? What if it redesigned the entire factory that stamps the wrench?
Yeah, and then went a step further, completely rebuilding the machine that designed the factory in the first place.
Exactly. So, welcome to today's deep dive. We've got a stack of research mapping out a massive leap in AI capabilities. I mean, you usually hear about AI prompt engineering, right?
Right, just tweaking the text.
Yeah, tweaking the text. But today we're looking at what happens when an AI bypasses the prompt entirely and just starts rewriting its own core programming.
So for a long time, self-improvement in AI relied on text.
Yeah.
You edit the prompt to the memory, but text is, well, it's a soft medium. It drifts.
It's fuzzy.
Right, exactly.
Yeah.
If you have a fundamental flaw in the AI's core routing logic, changing the text prompt just won't reach deep enough to fix it.
Okay, let's unpack this for everyone listening. Relying on text to improve an AI is, well, it's like giving a struggling employee a really good pep talk. You're nudging their behavior with a suggestion, but suggestions can easily be ignored.
Yeah, they often are.
Exactly. So today's research introduces a system called MOSS. MOSS doesn't use text at all. It lets deployed agents rewrite their actual source code, the underlying deterministic code. So instead of a pep talk, this is like rewiring the employee's nervous system while they're wide awake.
And that awake surgery problem is exactly why MOS has to be incredibly careful. I mean, if a system rewrites its own source code while running, one bad line could just crash the whole thing.
Right. Instant game over.
Yeah. So rather than blindly editing, MOSS creates a temporary disposable clone of itself. It attempts the surgery on the clone using a 7-stage deterministic pipeline, tests to see if it survives in a safe sandbox, and only if it works perfectly does it hot swap that fix into its live brain.
Wow. And it clearly works too. I mean, on rigorous software engineering tests, specifically the OpenCLAW benchmark, MOSS jumped from a 0.25 to a 0.61 score in just a single cycle.
It's a massive leap.
It is, but looking at our notes, I do have to push back a bit. MOSS has a catch. It actually hands the code changes over to an external coding agent CLI.
Yes, the external tool.
Right. It's not entirely doing the surgery itself, meaning a lot of that success rides heavily on the capabilities of an outside program.
That is true, and that limitation forced researchers to ask a bigger question, like, what if the AI didn't just fix its code, but rebuilt the factory that writes the code?
Moving up a level.
Exactly. That brings us to Hyperagents, specifically a framework called DGM-H. If MOSS is fixing the factory, Hyperagents are fixing the editor itself. They merge the task-solving agent and the self-modifying meta-agent into one single editable program.
So it's literally metacognitive self-modification. It improves how it generates future improvement.
Right, and it can create persistent memory and performance tracking that transfers across entirely different domains.
That sounds incredible, but here is where my skepticism flares up again. I mean, an agent editing its own editor. How do we even measure that? The research notes these hyperagent gains are mostly qualitative right now. Like, there are no hard benchmark tables proving this works safely yet.
Well, you've hit on the exact roadblock they faced. Traditional scorecards fail here. We literally cannot measure an agent editing its own editor using today's benchmarks.
It's just a totally different paradigm.
Yeah, and that realization forced the creation of a completely new scoring method to address what they call the meta-productivity performance mismatch.
That's a mouthful.
It is, but mathematically, it just means an agent's current benchmark score is a terrible predictor of its future ability to improve. If you greedily keep today's top-scoring AI and delete the rest, you inadvertently prune lineages that contain massive future potential.
Oh, I see. So if you just keep today's top scorer, you might accidentally kill off a lineage that would have produced an absolute champion, say, 3 generations from now. You keep the flashy kid and discard the one whose grandchildren would actually win.
That is the perfect way to visualize it. So to solve this, a framework called the Huxley-Gödel machine borrows a concept from biology, scoring by clade or lineage.
Scoring by its descendants.
Right. Instead of judging an agent on its current performance, you score it by the aggregated performance of its descendants. A mediocre agent that reliably spawns strong, adaptable descendants scores high.
Okay, so what happens to the test scores when we actually judge them this way?
The results are staggering. On SWE-bench Verified and Polyglot, this method beat prior models. When tuned with GPT-5 Mini and run with GPT-5, it reached estimated human-level performance.
Wait, really? Human-level software engineering?
Yeah, human level.
Oh, wow. So to draw the through line for you listening, we've moved from making safe text edits to AI rewriting its own underlying source code, and now to AI rewriting its own evolutionary rules based on the success of its descendants.
We're stepping away from direct control to gain massive operational reach. It's wild.
It really is. Which brings us back to that factory robot endlessly redesigning itself. It leaves us with something critical to ponder. As these AI models are increasingly selected based on the unseen potential of their algorithmic grandchildren, how will you maintain oversight when you're measuring a future you can't even see yet?